Hey guys, welcome back to M. Januar Says channel. In this video, I'm going to derive and describe the Drude model of conductivity. The Drude model can give us a simple picture of the microscopic behavior of metal basically. So finally, we can understand how electron move in a metal. That means we can characterize how good a metal. That's why later on this Drude model can come up with the description of conductivity. Let's start. Let's imagine we have a wire made of metal. This, if we enlarge the wire, it will look like a cylinder. Yeah, this cylinder. Maybe like this. Okay, so if we apply current to the cylinder, basically we apply positive voltage in the left side and we grounded the right side. So what we have here, we will have a current flowing from the left to the right. So microscopically we can observe that if we put maybe ammeter to this circuit, we will find that a current flowing from left to the right. But actually microscopically, what really moving is negative charge from right to the left, which is in this case bunch of electron moving from the right to the left in opposite direction to the current. So by definition, we can write down that current is the rate flow of charge. I mean the derivative of charge with respect to time. So basically, we can see from here that what really moving is electron. Yeah, from Drude model basically try to explain how this electron move basically. So how to do that? So we can see the microscopic uh, level of description. So basically what I'm going to do is I'm going to cut this cylinder to small volume. Let's assume that this volume have length of dx, because we just consider one dimension. Basically this direction is x basically, and the area, the cross-sectional area of this small volume, or maybe the same with the whole cross-sectional area of the wire. So let's assume the cross-section is a here, so that means the cross-section in here also a, because we assume the radius of the cylinder is all the same. And finally we can write down that the elemental volume, if the volume of the cylinder is V, then the elemental volume at this size actually we can write down as dV, which is equal to A times dx. So similarly, that means if the total charge occupy the whole wire is Q, that means the elemental charge occupying this volume can be written as dq, right? Then what we need to do is we need to find what is dq, and once we found what is dq, later on we can substitute to the definition of the current. Finally we can have more clear picture what is current in terms of charge. So basically, how much charge occupying in this small volume, we can assume that there are n number of charge occupying in that small volume, because this charge have charge. We need to time this n by e. E means the elementary charge. That means E will be equal to 1.6 10 to minus 19 coulomb. Because this is a negative charge, we need to put negative sign in here. And then because we assume that there is n number of electron occupying the small volume, then we need to times by dV. Then dq we can define it as the number of charge occupying the small volume. then we can write down that dv actually equal to a times dx. So we can write down this as NEA dx. Then we can have full definition of dq. So what we can do next is we can substitute dq to the definition of current here. So finally we can get that I equals to minus NE A dx dt. Then we can define that if dx is very small, so we can define that maybe this is will relate to, because dx dt basically equal to the velocity, right? But we can assume that this velocity as average velocity, because we assume that dx so small that finally we can get the v equal to the average of v, and what we call also the drift velocity vd. So we can write down minus NE A vd, where vd is, we define it as the drift velocity of the bunch of electron. Okay, finally we can define that the current density, basically current density, we can define it as J is equal to the current per area. So that means we can move this A to the left side. Alright, so finally what we get is NEVD. So then we can define that current density equals to NEVD. This is the drift velocity. Okay, but the question is, what is the drift velocity of electron? So to describe what is the drift velocity of electron, basically we need to go back to check in here, because we apply electric field, we apply voltage, what we get basically what they experience. If we pretend that we are charged, basically what we experience when this wire get a voltage, basically what they get, what they experience basically, because we apply positive in here, plus in here basically, and more grounded here, that means more negative in this side. So basically what electron experience, what they experience in between is that electron here, I will draw electron. So what they experience in here microscopically, basically they will experience some electric field applying to the charge. So this voltage will induce electric field from left to the right, so that the electron will experience Coulombic force. Actually, let's go to second page this way. So I will draw again to make it more clear. So we'll draw again here. So what they experience, basically they experience some electric field okay. Let's assume the electric field is E. So that means the charge will experience some electric field E. Finally they will experience force to the opposite direction. So we can write down that the Coulombic force in here is minus E. That's why we can see that the sign minus here make the force actually going to the reverse direction, to the opposite direction. Yeah, because this is vector, right? But because we working on one dimension, so we can omit the vector notation. Okay, yeah, because in here they experience force, so basically we can continue to connect this electric field, basically because this is force, they will create acceleration. Finally the electron will move to the left because they experience Coulombic force in this way. So finally what we should do, we need to use Newton's law basically, because this law correlate the force to the acceleration. But the problem is when they travel basically, because inside the conductor, this is not completely vacuum, not completely empty space. So that's why to completely describe the electron motion in here, we should consider that basically there will be atom surrounding the charge. So that's why this electron may collide to the atom. So because of this collision, there will be some friction there. So finally, this electron is look like some particle moving in viscous medium. So that's why there will be some friction. We can write down, we can assume that this friction will be proportional to the velocity. So basically, this is, we assume that this frictional force look like viscous force. So that means there will be some friction, damping in here, damping force or friction, that we assume that this is linearly proportional to the velocity. And then we can correlate this coefficient in here, we can correlate coefficient directly to the relaxation time. That means this is the time, that means before electron collide, basically they will be have certain time tau where this guy will relax before collision. That's what we call the relaxation time. This relaxation time will be inversely proportional to the damping. I mean, this is the decay rate of charge, because the electron will losing kinetic energy basically. So that they will decay basically. So that's why we can write down this B to be proportional to the gamma, the decay rate. But to make sure that the unit is correct, so we can add mass in front of them. So that's why we can write down our Newton's equation of motion equal to ma plus m gamma v. I omit the vector notation because we assume that this motion in the one dimension. Okay, so as we know, so we can write down that the a is the derivative of velocity. I can write down as v dot. Then finally we can simplify our equation, and also because the force triggering the motion basically related to the voltage, which is related to the electric field, that means the electron move because we apply electric field. So that's why we can write down the force basically equal to minus E, and then I can write down the A here directly to the derivative of v dot, and plus m gamma v. Okay, finally we can have the equation of motion for the electron under a constant